In the previous lessons, we talked about a very abstract mathematical apparatus of quantum mechanics and formulated the basic principle for quantum theory. Let's recall that now each dynamic observable of the physical system we associate with a linear Hermitian operator. Moreover, in the formula that we use to calculate any characteristics of physical system, not all matrices could be swapped with each other. Therefore, in order to produce any two operators, we must take into account their permutation of commutation properties. We also talked about the concept of physical state in the classical physics and the quantum mechanics, and we agreed that to describe the quantum mechanical states of the system, we will use the so-called ket vectors. In addition, we have already talked a little about the so-called pure states of the physical system. Today, we will talk about another characteristic type of quantum states of the physical system, which are called mixed states. However, before this, let us recall how we describe the pure states. First of all, we assign to each pure state a ket vector that is an element of Hilbert space. For example, if we are talking about the description of a physical system consisting of one qubit, then we will describe the pure state of the qubit using the ket vector, which consists of only two complex numbers. In other words, such a vector is an element of the finite-dimensional Hilbert space of dimension 2. Next, any sum of ket vectors of the Hilbert space taken with some complex coefficients is also a ket vector of this space, and it corresponds to the superposition state of the system. Since each ket vector included in this sum corresponds to its quantum mechanical state, this means that the physical system in the superposition state actually exists in all quantum mechanical states included in superposition at the same time. For example, on the slide, the physical system which is described by the vector psi will simultaneously be in the state of psi1, psi2, psi3, and so on. Recall that the complex expansion coefficients of these vectors are called probability amplitudes. Finally, the square of the modulus of each probability amplitude determines the probability with which the physical system, as a result of the reduction, passes from superposition to one of the states included in the superposition. So, for the ith term, squared modulo of Ci is the probability that the physical system from the superposition state will go into psi-I state. Let us now consider a statistical mixture of pure states, or, in a different way, a quantum mixed state. Often these states are also called the statistical ensemble of pure states. So, we have a set, each element of which consists of two components. We emphasize that, unlike pure states, mixed states cannot be described with the help of any one ket vector, and should be considered as a set of ket vectors with their probabilities. At the slide, we mark the first component of the set with a phi ket vector with some subscript, and the second component with the letter omega with the same subscript. Each of the omegas in is the probabilities with which we find the physical system in the corresponding state phi. And now we are talking about completely different probabilities in comparison with quantum superposition probabilities. To better imagine what type of probabilities it involves, let's turn to the following example. Let's imagine a box in which there are 2 red and 3 blue balls, and agree that these balls do not differ from each other except in the color. For simplicity, we'll also assume that nothing happens inside the box with the balls, and in particular they do not change their color. And besides, let these balls be macroscopic objects. Let us ask ourselves, what is the probability of getting a red ball out of the box? It is easy to show, dividing the number of red balls by the total number of balls, that the probability of this will be about 40%. We, however, are not interested in the number itself. It is important to add that each of the balls, even before we got it, had a certain color. That is, it could be either red or blue. Now, let's replace the balls with qubits, that is already some kind of microscopic object. Let us have 2 qubits prepared in the state 0 and 3 qubits prepared in the state 1. And just like in the case of the balls, we will assume that qubits do not interact with each other or with the box or with any other objects outside the box, that do not change their states. Then, if we get the qubit out of the box, then with a 40% probability we will get a qubit in the state 0, and with a 16% probability in the state 1. This is our statistical mixture of two pure states for a physical system consisting of 5 qubits. And probabilities, which we are talking about, that for balls or for qubits, belong to the same type. This is the so-called classical probability. The qubit that we got from the box, even before the measurement, is either in the state 0 or in the state 1. In this case, the reduction does not occur. This is a fairly simple example in which a mixture consists of two basic states 0 and 1. In the general case, the statistical ensemble can include any number of states, and not necessarily a basic one, and moreover, each of the states can be some kind of superposition. For example, in the case of the physical system consisting of n qubits, and 1 qubit may be in the psi1 state, and 2 in the psi2 state, and so on. In other words, if we get 1 qubit for such a system, then with probability omega 1 equal to n1 divided by n, we will get a qubit in the state of psi1, with the probability of omega 2 equal to n2 divided by n in the state of psi2, and etc. The sum of all probabilities, that is, the amount of omega 1, omega 2, will of course be equal to 1. To describe physical system in a mixed state, a so-called statistical operator or density matrix is introduced. For example, in the case when we have a set of pure state phi1, phi2, and a set of phi-n, then we can express the density matrix ρ in the form of sum over the index I of product of omega I and the projector to the state phi I. Note that the density matrix can also be used to describe pure states. For example, if the physical system is in the psi state, then in this case the statistical ensemble consists of only one element, and then the density matrix ρ will simply be equal to projection for the state phi. In the next lesson, we will talk about the density matrix element as well as its properties. That's all. Thank you for your attention.